Hello, welcome to my Lab 6 report. This is going over the metal tube drop. So, introduction. As you can see here, we've got the lab here on the left. And the point of this lab was to simulate what happens when a magnet is dropped through a ferocious metal tube, creating dipoles, or inducing currents that create dipoles to resist the force of gravity, causing it to fall at terminal velocity. In the system, in the experiment, the system is the magnet in the ferocious tube in Earth surroundings. So here we got some equations. First up, the dipole magnetic field, which comes from the magnet. And then as it drops, it causes a change in flux, which induces a voltage, which when you divide that by R, can find the current induced in the ring. Taking then the force of that, using this equation right here on the right, we can find out the force of the magnetic force, and add that with the force of gravity, figure out the net force. So here we've got the mu mag, found from lab 3, and then this is just some basic stuff. Now some steps that we took. So the first step is to calculate the magnetic field relative to the R. Then we have to calculate the rate of change by which the magnetic flux is going through as the magnet falls. Then we use that to calculate the induced current, and then we use the Biot-Savart law right here to calculate the force exerted on the magnet by the ring, and then we calculate the net force before finally updating position. And we just put that on loop and keep going at it. So over here on the right, we can see that we've got the blue and the red ring. And so blue is going counterclockwise. So when you use Lenz's law, you can see that would point upwards in the tube. And the red is going clockwise. And when you use Lenz's law, you would also see that it is going, is pointing upwards with Lenz's law as well. So then if you flipped the magnet, it would still be the same because the change in flux would be the same. So it would still act as if two magnets were repelling each other if you're looking at the two areas below it, and it looked like two magnets with one pulling one up above it. On the right, you can see this is mid-thing, so it's just looking like a regular slope. But on the bottom one here at the end, you can see it kind of curves upwards. That's the breaking from Lenz's law. So we know that the calculations are correct. It's just that the mu used was so small, it looks like it's just a flat line. And that hints more at a flaw in the previous lab rather than this code. Alright, so now what if the resistivity of the conductor was reduced to as close to 0 as possible? Well, if you recall, the induced current was found by taking the voltage and dividing that by resistance. And so as that gets smaller, that means the induced current gets bigger. And so if we get to the point where it's 0, it would mean the induced current would be practically infinite, which would mean that the force acting on the magnet would be infinite, which would mean that it's essentially just kind of standing there, because once it reaches equilibrium with the force of gravity and it's just standing there, there's no change in flux, which would mean that it wouldn't exert any more force past that. It would just keep enough to keep it stable. So it essentially just makes the magnet hang in the air as it decrease its speed as the current increases. Now, what if there were holes or slots in it? Well, that would disrupt the flow of current, which would cause it to be weaker, which would mean gravity would take over more. And in the case of slots, where it's just a line straight down, where there's no actual loop for the current to complete, which means that it would just not induce any current because there's no possible place for it to be. So for some sources of error, they could be human error, of course, in the act of carrying out the experiment. There's human error in terms of incorrect measurement of the tools, either the magnet or the tube itself being used, such as the thickness of the aluminum foil. And then, of course, as I mentioned earlier, there's possibly and most probably the inaccurate data from Lab 3. Thank you so much. I hope you have a good day.